Good evening, everyone. On behalf of the IEEE EMBS student chapter of University of Moratuwa, I'm thrilled to welcome all of you to this exciting session under Brainstorm 2025 in collaboration with our knowledge partner, Aura Digital Labs. Today, we are diving deep into a topic that sits right at the intersection of healthcare and technology. Advanced biomedical electronics and computational tools to overcome hardware limitations. Whether you're a Brainstorm competitor or just someone passionate about the future of biomedical tech, you're in for an engaging and eye-opening experience. Before we begin, a big thank you to the incredible partners who helped make Brainstorm 2025 possible. Our bronze partners, Excel Tech OU and WSO2, digital media partner HackSL, knowledge partner Aura Digital Labs. Your support is what keeps innovation flowing. Today, we are honored to have with us three brilliant minds from Aura Digital Labs who bring immense experience and insight to this field. Mr. Lasitha Haputantri, Mr. Sajitha Madugalla, Mr. Prabhat Vijaytilaka. From groundbreaking work in embedded systems to pushing the boundaries of computational modeling in biomedical devices, these experts have walked the talk, and today they are here to share their journey with us. So without further ado, I'd like to warmly invite our speakers to begin their session. Over to you.
Thank you, Manuri. We are a team from Aura Digital Labs, and today we are going to discuss about how hardware and software are correlated to each other. And I first like to invite Mr. Lasit Thaputantri to share his knowledge with you. Lasit.
Thank you, Sajitha. Hi everyone. Today I am unable to on my camera actually. Sorry for that. Once again, welcome to Brainstorm session on advanced biomedical electronics and computational technologies. I am Lasit Thaputantri, CTO and co-founder of Aura Digital Labs, and I am currently doing my internship on Magic Wheel. Okay, today we are here to share how technology is changing healthcare. Along the way, we will talk about hardware side like sensors, amplifiers, and filters, and the software side including digital signal processing, communication methods, and smart models powered by AI. Okay, let's dive. Next page. Sajitha, can we go to the next slide? Okay. Let's start how we collect signal from human body. Our body creates tiny electrical signals when heart beats, muscle moves, eye blinks, or the brain works. These signals are very weak and often noisy. So we use special tools to pick them up like sensors and electrodes. After picking the signal up, we amplify it to make it strong and filter it to clean. And finally, we convert it to digital form using a system called ADC, analog to digital converter. Okay, you can see the block diagram. This is how we prepare signals so the computer or the smart device can understand them. Okay. Let's go to the next slide. Okay, let's amplify the signal. Once we get the signal from our body, we need to boost it. Why? Because biosignals are very small and they can be easily missed. That's where the instrumentation amplifier comes in. It increases the difference between the two signals. So it ignores the common noise like electrical interference. And it has very high impedance, which means it does not disturb the signal we are trying to read. And so this is the best tool for cleanly and safely amplifying weak signals from the human body. Okay, next slide. Oh. Let's look common biomedical signal types. EOG, ECG, EMG, and EEG. These are very common biomedical signals. EOG are eye signals, and it's have very low frequencies, and it has very high amplitudes. So it is very easy to capture. And on the other hand, the brain signals EEG have very low amplitudes, like micro voltage levels. So this is very hard to capture. Okay, let's move to next. Okay. When we clean the signal, we need filters. So there are 4 types of common filters: low pass, high pass, band pass, and notch. As you can see, the low pass filters are only pass low frequency components. So it remove the high frequency noises. And you can, when you get a biosignal, if there are some, if you can see some noise like mountains, up hills, and so on, you can use a low pass filter. So then you can get the envelope of that signal. And when we look the high pass filters, it removes the low frequency components and pass the high frequency components. So let's get an example. You need you need 20 up from 20 hertz from up signal, and there are some low frequency like 10 hertz signals inside your biosignal. So you can use a high pass to remove that low frequency components like 10 hertz something to get your desired signal. Okay. On the other hand, with the band pass, it only pass some kind of band of frequencies. Let's say you need the signal to be 10 to 50. So you can design a filter to filter that can pass 10 to 50 hertz signals. Okay. And the notch filter, we use notch filters to remove the power line noise. You know that the power line is 60 hertz AC signal, so it will be affected to our biosignals. So we use notch filters to remove that. Notch filters are basically remove one frequency from our entire signal. Okay. Shall we go to the next slide? Okay. When we design filters, there are mainly two methods, analog filtering and digital filtering. And when we look analog filtering, we can design it using resistors, capacitors, sometimes op amps make them active filters. So analog filters filter the signals real time. So it is very fast actually, and it happens before digitalize the signal. So it is happening before you send the signal to the processing unit. And it is very power efficient. So it is great for wearables because wearables should battery powered, and they have some limited battery supply, power supply. So we need to careful about the power. And but unfortunately, analog filters cannot change after build it because we have physically made it. And on the other hand, digital filtering is a code we written on a microcontroller, MATLAB or Python. And since it is a code, we can write it over and over again. It can change after build it. Yes. Okay. Yeah. Can we go to the next slide? Yeah. Now we got the signal and we filter it, amplify it, and we need to send it to the processing unit. So, but we didn't use the sampling. Yeah, we need to use ADC to convert our analog data to digital data. Why? Because the computer cannot understand the analog signals. It only understand the digital signals like 1, 2, 3, and it only understand the numbers. Numbers mean bits. So we need to convert the analog signal to digital signal. That's why we use ADC. In the ADCs, we usually sample the analog signal more than twice from its frequency. That is the Nyquist theory. Because otherwise it can be missing some data from our analog signal. Okay. Now we have the digital signals, and we need to send it to the our processing unit. It depends on the application, and you can use Wi-Fi, Bluetooth, LoRa, or UART, even UART communication. It depends on the application actually. If you use wearable, you can use Bluetooth, NRF, and so on. And for much larger setups, you can use Wi-Fi. So it has a bigger range that you can communicate. If you use LoRa, it is very you can go very big distance. Okay. Can you go to the next slide? Okay. Now we send our data to the processing unit. Now what we can do? Now we can do everything. Yeah. Now we have the biosignal. Now it's matter of the machine learning or monitoring or that kind of problem. Now you have the data, and after that part, it is not a biomedical task. It is actually biomedical task, but it is not depend on the biomedical, because we got the signals from the user, and now it's data communication, and machine learning part. So we can use this data to real-time monitoring like health monitoring, or we can build data sets. You know that when we use machine learning like classification models, we need some data sets. So we can make data set using that signal. Or by using that data set, we can train machine learning models and predict health analysis. And we can develop some smart devices. The possibilities are endless. Yes, I think you have some basic idea of how to get biomedical signals from a person and send it to the machine learning part. So now over to you, Sajid.
Okay, thank you, Lasit. And I hope I am audible. So, like, I'm pretty sure that Lasit has already shared some of his hardware knowledge with you. Honestly, he's one of the best hardware designers I know. And of course, he's the best hardware designer in our company. Anyway, I'm Sajitha Madugalla, currently working on an assistant research student at the University of Sydney, Australia. And I am the finance officer in Aura Digital Labs. So you are all about to take part in Brainstorm event, as I know, and I'll be introduce you to some cool technologies related to medicine and biology. So we can start with a simple question, where the technology is. So I know you know what these pictures are. These are few examples for biomedical devices. First up, we have this ECG machine. Uh, it's like it's like pick your biosignal from your body and process them and display a clean waveform that reflects your heart activities. It's a simple idea, but incredibly valuable in practice. With the things Lasit shared with you, you can even make one of these, a simple one, not a complicated one. And next we have a fall detector. Most of the elder peoples need one of these when they are like alone at the home. It's just an accelerometer. When someone falls, actually they fall with the gravity. Okay, and it's a straightforward concept. We can measure the acceleration when someone is falling to detect a fall. So this is a simple concept, but it's valuable in when it comes to life saving, and it's quite impressive. And this the pulse oximeter is a popular device from the COVID season. With just two LEDs, it can measure the oxygen level in your blood. So these are just few examples from the world of this biomedical technology. These are like these are like very bulky, but it's very accurate. But like the latest smartwatch have all of these devices. Like they can measure your heart rate, your speed, and even come with the latest one come with the built-in ECG apps. So it's like carrying a mini medical lab with you. If you're someone who runs regularly or just wants to stay healthy, having one of these is almost a must in these days. This is where the technology is heading. It's compact, smart, and super user-friendly. And that's the kind of thinking we are looking for from you all. Creative ideas that blend technology with real-world needs. when we talk about the wearable electronics, there are so much more to explore. You can see almost every wearable things are like related, the come with technology, electronic technology. As for example, hearing aids, smart clothing, even electronic tattoos are all part of this growing field. So as someone who's worked closely with the IEEE Engineering in Medicine and Biology Society, of course, the team behind this event, I have seen some really cool innovations. For example, when we like talk about these smart clothes, there was a wearable vest that could monitor heart activity. It was um, from Peradeniya University of Peradeniya team. We can't say like he's wearing a vest. It's very compact and it can measure your heart activity. Also, a team from our company also once participated in this brainstorm in a past brainstorm iteration, and we won the second place for a small pair of smart spectacles that we design. It can monitor EOG signals and do some uh, detections, sleep detection. And if you are curious about something really like futuristic, you can search Tacto. It's a project by Dr. Anusha Vitana, who also my supervisor in these days. It's a smart tattoo that you can into your skin. It like not inked actually. It's kind of a tattoo. It can give you some feelings that you already feel. So there are even more advanced technologies out there. Like for example, pacemaker. It's like an implant device. So if you are planning this kind of devices, there are so many regulations you have to think. There are some ethical considerations also. Anyway, it's a small device that monitor your heart activity and send electrical signals when it detects a slow or like irregular heartbeat. Like your heart is work with a small electrical pulse, but if your heart is not healthy, like it can't generate the required electrical impulse to work as normal, these pacemakers can generate those impulses artificially and make your heart work, which is life-saving for many people. And it's not just about hardware. Like there are some amazing software applications making a big impact in healthcare too. Like one of the great example is virtual reality. Medical professionals can now like train before a heart surgery. You have the environment, the whole environment around you. Like you have the tools, you have the whole environment, and you have even a virtual patient. So you can simply put the VR in your head, and with some tools, you can use that like virtual medical tools. So these are very helpful for like medical professionals when they are doing critical surgeries. They can even practice before doing the surgery for the actual patient. And the device here is a haptic device. This haptic technology is actually you can feel the tools you are using in the virtual world. It's really associated with those VR technology. You can see the medical professional here, maybe a doctor. She's using a pen-like device here. Hope you can see my laser. A pen-like device here, and you can see the screen. This is where the surgery happens. This is where the surgery should happen, and she can actually feel the syringe. Like she can practice the whole surgery in this device, we can get the feeling, the actual feeling that we will have from the surgery. So these haptics are very helpful for doctors. So the experiences feel real, so they can practice before they face the surgery. And tactile sensors. These are just force sensors, and these are just force sensors and temperature sensors. These can be used to give the feeling we have to the computer. It's like think like we can touch some like we can touch something, but only we can feel it. But how you could give that signal to the computer? So this concept is just a few force sensors, and you can give the signal to the computer. It's like a input. So and also thermal sensors. It can sense the thermal activities like we feel with our hands or skin. This is how you can use the technology. Like think it's like not think it's like a technology, just the technology. You can relate it to our own body activities. So these kind of applications can be done with those tools. And I just talk about the existing technology that we have, and let's talk about where the technology is really heading. Actually, from the competitors like you, we want you to think and go to the future, because that is where the technology is going. So you like it's not good, like you can't do like it's not working like that. Yeah, that you can repeat the existing technology. You have to think to the future and make something that will do a huge impact in the future. So we have this AI powered diagnostic devices, like maybe AI continues to advance. Like it's clear that the future diagnosis will be partially powered by AI. Of course, we can't give full control to the AI in this medical field, for especially for ethical reasons. It will play a huge role in assisting doctors with diagnosis. Actually, right now, we already have AI algorithms that can detect cancer or identify anomalies in medical scans, like CT scans or something. They only need the few pictures of CT scans, and they can detect um, anomalies in those images. In the future, AI will work alongside these medical professionals, helping them make faster and more accurate decisions while still keeping the human touch in care. Actually, we can't replace the whole medical diagnosis with AI. Like we can't give the life of a human to a whole machine, but we can help medical professionals with the technology we have. So that is how the AI will help to this medical field. And we have smart prosthetics. Like think of a disabled person. We no, just think of yourself like I can move my hand like this with my brain signals, but a person like a disabled person without a hand, he can think, but he can't move his arms. And also if he is born without a hand, he never know how to move a hand because he never had those feelings before. So that is where smart prosthetics comes, and smart prosthetics will help to disabled persons to get the experience like us, same like us. they can do with their artificial hands, anything with their artificial hands. And this flexible electronics technology, if you are making something wearable, these kind of flexible electronics must be there, because you have to think the comfortness and how compact is your device. If you are like hope to make one of these flexible devices, you can actually get those printed flexible circuits from Chinese companies. I don't like to just say the name. You can search for it. Actually, most of you already know the company. With that, you can even get the flexible circuits. So if you are planning to make a wearable device to this competition, I suggest that you should try those flexible electronic circuits. So you will have more credits for that. And this is like kind of a device that use those flexible electronics. You can see how compact they are, and think like if you are wearing this, you can easily move your hand without knowing like you have a device on your hand. So it's very comfort to the user, and also very compact. You can use it as you like daily use. And you all know who this is. This is Elon Musk, and he has developed a device called Neuralink. This technology, but this technology has faced significant ethical concerns. Like
හොඳයි කිව්වේ නෑ අර නිකන් කිව්වහම
sorry. Okay. As I said, this technology has faced significant ethical concerns. Actually, it is halted, like restricted in the medical field for now. It's a good example of how technology can push the boundaries of what is possible, but still we need to cautious about the implementation. It's like these are like implantable devices. If you think you can go with an idea with these implantable devices or something very something can be dangerous to our body, you have to think ethical considerations, and many regulations are there. So I don't think if you can compete competition like this with those implantable devices. So if you plan to do something like this, you have to think more about those regulations and stuff. I think you will be you will have some sessions about that in the future. And we have the technology, and we have some idea about the future technology. And the thing is, what can we do with this technology? Technology is just a tool. We can learn it. We can even search for it. There are so many technologies. Like it's like a it's like a huge thing. Technologies, like there are something we never saw. But the most important thing is the idea, and the goal you are trying to solve. First, you have to have you must have a good goal, like what you are trying to solve, and generate idea, so you can solve that goal. To solve that goal, use technology as a tool. So it's only a tool. There are so many technologies are there to achieve your goal. First, generate a good idea, so you will have end up with a good product. And we actually just talk about the hardware and stuff. Let Give me a minute. We have the technology as a tool. Just make a good idea first, then you can achieve your goal. Like we already talk about the hardware stuff, and there are many technologies you can use. Just use them and learn them, and like generate new ideas to solve real world healthcare problems. And the existing hardware technologies have their limits. You can't, like, as an example, instrumentation amplifier, it's a way to get biosignal from your body as a analog or digital signal, but it has limits. Like it can get a biosignal from your body, just that. If you are like want to get something from it, like if you want to do a diagnosis, or if you like to do a detection, you have to interact with hardware with some hardware with some software tools. So software tools also a must. If you are like, is don't just make a just hardware. You can use software tools to add the value for your hardware, because there's a limit to hardware. So to talk about those software tools and how to like interact with hardware with using software, I like to invite Prabhat to talk about software tools. Prabhat.
Yes, thank you, Sajid. Yeah, hope you can see and hear me. Okay. As previously introduced, I'm Prabhat Jethil, director and co-founder, and also CEO of the Aura Digital Labs. And I'm currently doing my internship at London Stock Exchange Group as a hardware accelerator system engineering. First of all, I would like to thank EMBS to give this chance to our company. Okay. During this session, Lasit and Sajita describe how hardware behave in biomedical field. But as you all know, and as Sajita described, there are some limitation in the hardware. Okay. Now I'm going to discuss with you how we can use computational tools to overcome this hardware limitation. During my part, I mainly focus on how we can use machine learning and deep learning. Actually, how we can play with machine learning and deep learning in the biomedical playground. Then how we can use generative AI. In those days, very famous, I think. How we can use generative AI to push boundaries in machine learning to generate synthetic biomedical data sets. And finally, how we can apply machine learning and refine a main signal by using a second signal. That's the main subtopic. In the first two topics, I am going to discuss some theories and ideas. And the latter part, I will give some idea how we can apply those things to the real world application. Okay, Sajid, let's go. Okay. Machine learning and deep learning. I hope you all heard the word machine learning and deep learning. Definitely it should be. Okay. With the machine learning application, the main issue I think is the data processing and find the data set. So yeah, we can actually we can use generative AI and some stuffs to generate data set. I will describe it in later. Okay. Mainly, we can use machine learning in the biomedical field to do disease prediction and drug discovery, medical image analysis, that kind of intelligent healthcare application. Recently, NVIDIA also introduced a new tool to actually tool set to help how increase the speed. I mean, how increase the process of drug discovery. Actually, it's some kind of masterpiece. You can find it from if you are interested, you can find it from Google. Okay. By using machine learning and deep learning, we can do some pattern recognition in biosignals, real-time decision making, and very important part. The very important part when bridge between hardware and software is noise filter. We can do that also by using machine learning. Okay. In the machine learning pipeline, there are mainly 5 stages. As you can see, define problem, create data set, data pre-processing, develop the machine learning model or deep learning model, and finally, evaluation. For evaluation, there are a lot of evaluation matrices, and yeah, I will describe in later. Yeah, the machine learning is a key concept. I mean, for in biomedical field, there are lots of application. There are a lot of application uses machine learning and deep learning. So in your project in this competition, I highly encourage you all to, if you have any chance, please try with those things. Okay, Sajida. Okay. Machine learning and deep learning. What is the difference between machine learning and deep learning? As you can see, according to the chart in this slide, definitely deep learning is the subset of machine learning. The main difference between deep learning and machine learning is we have to manually extract the features. Features mean if we have a data set, there are a lot of features according to the problem. So we have to do feature extraction in manually when we use machine learning, and then feed those data into our model to further process. When we use deep learning, actually we can it's automatically learn the complex pattern from unstructured data using multi-layer neural networks. This is the main difference between machine learning and deep learning. As listed down here, there are some machine learning, many machine learning model and deep learning model. Like when we talk about machine learning, there are supervised, unsupervised, clustering, classification, reinforcement, association, rule mining, that kind of. There are a lot of models are there. You can find when you are Googling. And when we talk about deep learning, the key component in deep learning is neuron. Neuron. So there are fully connected neural networks, convolution neural networks. We can use convolution neural networks when image processing kind of things, and GAN, generative adversarial networks, MLP, multi-layer positrons, and encoders, and many more are there. So if you interested about this, there are plenty of resources in the Google. So you can search and apply your application. Okay, Sajid. Okay. Let me explain a small example that we can actually apply our machine learning and deep learning kind of algorithm to the real world application. This is the ECG anomaly detection application. In traditional machine, they use threshold based or rule based methods, but it can miss some patterns, or it have some limitation in noisy environments. That kind of issues are there. But when we use machine learning and deep learning for detect anomaly of ECG, definitely its accuracy is more higher with compared to traditional approach, because those models learn from large data sets, as I described previously. Those ML and DL model are learned from data sets. Therefore, those can predict with high accurate as well as some real-time inferencing for suitable for your application. So this is a very important thing. I mean, real-time and high accuracy is very important in the especially biomedical field. So we can apply ML and DL concepts to the ECG anomaly detection. As you can see in the top of this slide, there are two graphs. Both of them are ECG. But in the second one, there are some anomalies. In first one is a usual ECG wave, but in second one, there are some anomalies. If we have already trained some model, we can definitely identify those anomalies according to the pattern. Okay. Okay. But there are some limitation as well. But when we talk about signal capturing, especially signal capturing, there may have some noises. And also, if we use machine learning application to the existing system, existing signal, we have to reduce. We should try to reduce the noise, because it may affect the accuracy and misprediction. So there are few challenges happening because of motion artifacts and electromagnetic interference. Actually, motion artifacts is the common ECG disturbance that refers to ECG tracing that are not related to heart electricity activity, but rather to patient movement or other external factors. It can distort ECG baseline and those waveforms. So to eliminate that, we have to use denoising autoencoders or defilters, that kind of things we can apply. After the apply those things, we can obtain clean signal for analysis and monitoring for our purpose. Yeah. Sajid, can we move next? Okay. Let's assume we have already developed some machine learning model. Now we have to deploy that model onto edge devices. We have to deploy on in the edge devices. There are plenty of sources. In here, I would like to actually talk about TinyML. I hope it's bit new things for you. That's why I took it here. TinyML is a small Arduino kind of board, but we can add a machine learning model, train model to this board and get some inferencing. There may have some, sometimes users have to do some quantization according to the resources and according to the model. By the way, we can actually feed the model to that kind of TinyML boards. Yeah. Since we came very close to the edge devices, I would like to talk some big things about some hardware accelerated things as well. So if we want some speed up inferencing or some kind of speedy output, you can profile your machine learning model and identify which part of the model are much overloaded. According to that profiling, you can design some accelerating circuit or accelerating design, and then you can accelerate the your model. It will then it will produce your it will inferencing, it will train very fastly and accurately. There are a lot of ways to accelerate. Yeah. Okay. Then next slide. Okay. So far I have talked about actually how machine learning and deep learning things apply to the real biomedical application. Now, as I said at the beginning of my part, the main issue and main bottleneck of the machine learning and deep learning kind of application is the generate and generate to observe the data set. In biomedical AI application, especially biomedical AI application, it needs high accuracy. So those need massive and diverse label data set. But there are limitation in real world to collect that data sets because of some privacy concerns. There are some regulations as well. Yeah, there are some regulations, and also some diseases are very rare. So therefore, it has limited access to collect those data, and also high annotation by experts, and also because of the imbalancing, it may have biased the output. So bias and imbalancing in the existing data set also a huge problem. So we can therefore we can apply generative AI to bridge this gap between the synthesize and high fidelity realistic biomedical data. I mean that we can observe some data sets in synthetically we can observe data sets. Yeah, let's see how. Sajita, can you? Okay. There are a lot of generative models, but today I am just going to talk about 3 models: GAN, variational autoencoder, and diffusion model. I very much sure most of you heard the diffusion word rather than GAN and variational encoders. Anyway, let's talk about each one of those. GAN. GAN means Generative Adversarial Network. It has mainly two parts: the generator and discriminator. Okay. The generator learns to generate data. After that, the discriminator learns to distinguish the generator's fake data from real data. As you can see here, there are in the image under the GAN, there are two main paths: training set and random noise. We can generate some fake data from the random noise. We can feed some random noise to the generator and generate a fake image. And also there is a training set. Those are the real image. Discriminator compares those two and we can generate some more data set with from small data. It is one way to generate some data set. Then we talk about variational autoencoders. Variational autoencoders that compress input data into simpler elements. The encoder does that part. Encoder does the compressed input data into simpler elements. And the decoder that reconstructs the original data from its compressed elements. Okay. And also there is a probabilistic latent space where each input data point is mapped into the distribution of point in the latent space. You can see how variation autoencode works by referring this diagram: encoder, decoder, and probabilistic latent space. Okay. Then we talk about diffusion model. There are a lot of diffusion model in now some open source and some large language models. DALL-E is OpenAI's diffusion model. Anyway, diffusion is some kind of weird idea. It means, as you can see, there is two process. Forward diffusion process and reverse diffusion process. Actually, let me take like in this way. Imagine an image slowly corrupting an image or signal by adding random noise. An image slowly corrupting by adding some random noise. It happens in the fixed forward step. An image, it produces some noise. Finally, it is totally a noise. Then training a model to reverse this noise step by step to produce high quality synthetic data from pure noise. I mean, in the reverse process, we can generate a real image from starting a noise. That is a diffusion model. So if you have already trained a model to reverse denoising process, we can generate a model, we can generate images or something from a noise. That's why I told this is some kind of weird thing. So those are just only three. There are a lot of generative models. Yeah, if you are interested, definitely you should you can search from Google. Yeah. Okay, Sajid, let's go. Okay. NVIDIA. Actually, I think you may heard about NVIDIA. Yeah. NVIDIA. There are plenty of discussion about NVIDIA stock price when deep seeking introduced. That's why I talk about like this. NVIDIA is a company. They mainly producing GPUs. There is a NVIDIA tech stack. Okay, some of tools from this tech stack can use to generate synthetic data sets. Some are NVIDIA NIM, NVIDIA Omniverse, Cosmos, those. Actually, 3 of those are cutting-edge platforms that can be used to generate synthetic data sets, including health and life science and application. Okay. Let me show a small video about NVIDIA Omniverse and Cosmos, how it works. Yeah, and also NVIDIA NIM. Can you show Sajid?
NVIDIA Omniverse to build physics-based, geospatially accurate scenarios. Then output Omniverse renders into Cosmos, which generates photoreal, physically based synthetic data. Whether diverse objects or environments,
Okay. As you can see, we can use NVIDIA Omniverse. Yeah, we can use NVIDIA Omniverse to generate some build some physical scenarios. Cosmos will give me. Yeah, Cosmos will generate photorealistic physical based synthetic data. Yeah. Then there is a small clip about NVIDIA's NIM. Sajid.
generative AI synthesizes amazing images from simple text prompts. Yet image composition can be challenging to control using only words. With NVIDIA NIM microservices, creators can use simple 3D objects to guide AI image generation. Let's see how a concept artist can use this technology to develop the look of a scene. They start by laying out 3D assets, created by hand or generated with AI. Then use an image generation NIM, such as Flux, to create a visual that adheres to the 3D scene. Add or move objects to refine the composition. Change camera angles to frame the perfect shot. Or reimagine the whole scene with a new prompt. Assisted by generative AI and NVIDIA NIM, an artist can quickly realize their vision.
Okay. As you saw, by using generative AI and also NIM, we can create this kind of huge data set for our training purpose. Okay. Then we reach our last topic. Sajid, next slide. Okay. This is the last topic that I am going to discuss with you. In here, we can actually use secondary signal to improve accuracy and reliability of main signal. As I said previously, the signal capturing will be disturbed because of noise. So therefore, we can capture another signal alongside with the main signal, we can mitigate that interfacing effect somewhat level. Yeah, this happen because of noisy and dynamic environmental areas. So as you can see here, we can capture ECG signal with the accelerometer signal. Then we can remove the motion artifacts of motion artifacts during the moment. In there, yeah, how it happened, I will describe in next slide. As you can see there are a lot of signal capture side with other signal. Then I mean EEG, EMG, PPG, skin temperature, GSR, that kind of signal couples we can capture, and then it will mitigate some external effects that affect to the main signal. Okay, next slide. Okay. Sorry, I think I have some connection issue. Anyway, I think you can hear me now. From which part I have to?
Maybe it's better you start with the beginning in this slide.
Okay. Okay, sorry for that. Anyway, let's continue. I was talking about collecting a secondary signal for refined main signal. There are few techniques to signal fusion. Those are some of those are Kalman filtering and multimodal deep learning and machine learning application. Those are, I mean, in Kalman filtering, we can predict through signal state using both main and secondary signal. The special thing in Kalman filtering is we can generate a through signal, I mean predict a through signal in real time. In most of cases, some in robotic application, we mostly use Kalman filter for error correction. Yeah, and in machine learning fusion, it combines handcrafted features from multiple signals using traditional algorithms like support vector machine, random forest for improved decision making. Finally, for deep learning fusion, it automatically learns and integrates complex patterns from multiple signals using neural networks such as CNN, LSTM, that kind of things. For an example about machine learning fusion, we can combine heart rate signal with skin conductance plus motion to classify stress of a person. That kind of things we can do. Yeah. Finally, at last, we can combine two signals and get a better main signal. We compare those two signals. Okay, sir. Next slide. This is a simple example that where we can use this method. I previously also discussed this one. We can collect ECG plus accelerometer signal in Then we can apply some machine learning or any approach. We can filter out clean heart rate during the motion. As you can see there, original EOG signal is in blue color. It includes both motion and ECG signal. If we apply some high pass filtering, we can eliminate the motion artifact in part and only get the original ECG signal. Yeah, that is one example that where we can use double signaling for signal capture. Yeah, that's the only whole thing that I am going to discuss today with you. Yeah.
Okay, and it's like a huge domain to describe in 1 hour, 1.5 hours. I'll give a like brief summary for what we are discussing today. It's like you are facing a competition here, and we need from we need like the world needs some very good ideas from you. So the first thing you have to get is a strong idea. Then you have to have a good goal. You have to have a good end goal. So to uh, go from your idea to the your end goal, use technology as a tool. We just discussed about the technology here. Actually, you can learn technology from anything, anywhere. If you are like dig deeper, you can even make new technologies, or you can use the existing technologies to overcome the like medical challenges in the society. So that is what we are expecting from you. Not just make like totally hardware thing. Just combine software tools with your idea, so you can end up with a good product. Like as an example, it's a simple example. This is the Medibox. The Medibox is a very popular product, like a popular thing in these kind of competitions. Like it's a device that can sort out tablets, tablets from a collection of tablets. Of course, you can divide those tablets with their sizes. It's totally hardware project. You don't need to use software tools, but there are same shape. There are some tablets which has same shapes, so you can't divide them just with the hardware setups. You can use a camera to like see what the tablet is. The tablet has colors and some letters engraved to it, and you can use a camera to divide those tablets which have same shapes. It's a simple idea to use software tools to improve your project, and that's we are just talking here. Just don't stick into just hardware. Use some software tools so you can end up with a better product. So I hope you guys have some knowledge from our session. I think we shared some technology stuff. Actually, you can again, I said you can learn these everything from some external tools. You can just browse them, or you can just have a look in YouTube or something. You can have this technology knowledge from those sources, but the important thing is your idea. Just make the best way, best technology, choose best technology to achieve your goals. So thank you. We are happy to ask your questions if you have any questions. Thank you.
That was truly an insightful session. Now let's open the floor for questions. Please unmute yourself or drop your questions in the chat.
Before sensor fusion. Sensor fusion means give me a minute. Okay. We have one question. Could you please show the slide before sensor fusion? Sensor fusion means what do you mean? Is it related to hardware? Okay. This one, right? Yeah, do just like I was thinking you just need to have a look, or like you have any question with that slide? Yeah, okay.
So is it a direct message? I couldn't see anything.
Uh-huh.
Can you hear me?
Yeah, sure.
So my
Yes,
question
Luchita.
is, like, when we are implementing filters, like how do we like find when to use like digital filters or analog filters?
Actually, Luchita, you can use only digital filters. If you are like, it's really depends on what you are trying to do. You can just make a circuit with analog filters and get a biosignal from it. You still have some unwanted things in your signals like motion artifacts. You can't just ignore motion artifacts from analog filters. You can, but you will miss some of the important things when you are filtering out those motion artifacts. So you can use digital filters and also some machine learning tools to remove those artifacts and interferences. The thing is, like if you are, let's think, if you are like thinking more about the compactness of your circuit or of your device, just use digital filters, so you can do all those in the processing part. If you like more think about the features of the signal, you have to use both analog and digital filters. It really depends on you what you are trying to do. I think I answered your question, Rajendra.
Yeah. Thank you, Aya.
If you have any tiniest doubt about today's session, now is the time to clarify them. So ask away your questions. To our bronze partners, ExcelTech OU and WSO2, our digital media partner, HackSL, and our knowledge partner, Aura Digital Labs. To all our Brainstorm 2025 participants, today's session might just be the spark that takes your project to the next level. So until next time, keep innovating, keep exploring, and keep brainstorming. Thank you.